All right, so we're going to pick up where we left off in 6.4 yesterday. We just talked about how adding a multiple of the period does not affect the answer. And for tangent and cotangent, remember the period is pi. For all the other trig functions, what's the period length? 2 pi. Yeah, 2 pi. So we've talked about the transformations with sine and cosine, how you can put a number, the a, the b, the c, and the d in all those different spots, and it will affect how the graph looks. All the transformations with tangent, cotangent, secant, and cosecant are exactly the same. So can someone remind me, we'll start with a. What would a do? What kind of transformation? Yeah, which kind?
Horizontal.
Which one?
Horizontal.
Horizontal. What about b?
Horizontal stretch.
Yep, so A and B are your two horizontals. C and D are the two verticals. So A, remember if it's positive, it would shift it to the left. A negative would go to the right. For B, if B is a big number, like 10, does that stretch the graph 10 times as much or make it 10 times more compressed? Yeah, compressed. Okay, the bigger you make B, the more compressed the graph gets. The smaller you make B, the more stretched it gets. For C and D, it's not backwards. If C is a big number, it will stretch the graph bigger. A small number will compress it smaller. For D, a positive number would shift it up and a negative would shift it down. If the B or the C are negative, we just did one where C was negative in the homework. What does the negative do? Causes a flip or a reflection. If the B is negative, that's a horizontal reflection. Okay, that means your graph would do something like that. All the x's would become the opposite. If C is negative, that's a vertical reflection. That means all the y's become the opposite because it flips up to down. So any question on what the A, the B, the C, or the D would do? And we're looking at them all together because we're not going to go into as much depth as we did with sine and cosine. All right, so if we want to find the period of the tangent or the cotangent function, we use the formula pi over b. With all the other trig functions, we use 2 pi over b. Okay, so it's a little bit different formula for tangent and cotangent because the period is pi over b. If you want to think of it kind of in general, the formula to find the period of any trig function is the original length over b. Pi is the original length for tangent and cotangent. Any question on that? All right, so now, let's just say, I'll give you an example. Let's say 4 tan 2x plus 3. Okay. If I asked you to list the transformations, what would be the first number you would focus on? The 2, the 3, or the 4?
2.
Yep, the 2. And what would you say the 2 does?
Horizontal stretch.
Yeah, it's going to really, you could say it 2 ways. The 2 is going to make it more compressed. So you could say stretch by a half, which technically would mean to compress. Or you could just say horizontal compression by a factor of 2. Okay, so we got that one. What would be the next number we would look at?
4.
A 4? And what would that do?
It's the vertical Vertical stretch.
Yeah, vertical stretch
By factor of 4.
by factor of 4. And the last thing, the +3.
Vertical shift going up 3.
Yep, so shift up 3. Okay, so if I asked you to describe the transformations, that's how you do it. And what if I also, just off to the side, what is the period? Pi over what?
2.
Pi over 2. Because the formula you use for tangent is pi divided by b, not 2 pi divided by b. That's for sine, cosine, all the other ones. Okay, any question on that? All right, now, the next thing, I think I'm going to do something, I'm going to come back to that. Okay, I guess we'll do this real quick. We kind of already did that. So tan 2x is exactly the same as what I just had. So the period is pi over 2. But what they want you to do that's extra is set up a window on the calculator that shows exactly 3 cycles. Okay. Well, if one cycle is pi over 2, how big is 3 cycles?
3 pi over 2.
3 pi over 2. So the easiest way to set up a window that has a width of 3 pi over 2 is to just go from 0 to 3 pi over 2. Okay? Any window that has a width of 3 pi over 2 will work. That might not be the nicest window. We might end up cutting a cycle in half. So you might end up with like a half, a whole, and a whole. So you'll end up with 3. But we might cut one in half. Okay, plug in your graph. And if we set the window correctly, we should see 3 cycles. And we are going to see a half, a whole cycle, and a half. But technically, that still is 3 cycles. Any question why that's 3 cycles? Okay. All right, so I think we did everything. Find the period and find a viewing rectangle that shows 3 periods. You would just write down all your mins and maxes. Min and max aren't all really important with tangent because it's going to go up and down forever. So, I mean, as long as you set it like -4 to 4, -5 to 5, you're going to see enough. Right? I wouldn't do like -200 to 200. It's going to zoom it out so much you're not going to see the curve very well. Okay, so something like that is a good window. All right, so now, kind of connecting to transformations. One of these is the graph of 2 tangent x, and one of them is the graph of 5 tangent x. I just want to identify which one is which. So if you know what the 2 and the 5 do, you should be able to tell.
The 2 is the smaller one, the 5 is the bigger one, right? Or no?
Can you explain it in a different way?
2 is on the right, 5 is on the left.
Yeah,
Because
that works. Yeah.
5 looks like it's been pulled up and down more.
Yeah. The 5 tangent x has had more of a vertical stretch to it. So think if you had like a piece of metal that had a bend in it, you keep pulling on it. The more you pull on it, the more it's going to start to straighten out. It's not going to have as much of a bend in it. So this is the one that's been stretched more. The one on the right has not been stretched as much. Any question on identifying which graph is which based on the 2 pictures?
So the bigger the number on the left, the more stretched it is?
Yeah. Yep. I mean, it would be kind of hard if I said, like, here's the graph of 19 tangent x and here's the graph of 20 tangent x. They would look so similar. That'd be hard to tell. But I think with 5 tangent x and 2 tangent x, it's it's pretty clear one of them has more of a bend in it than the other. Okay. All right, so now let's look at secant and cosecant. Secant is the reciprocal of which trig function? Anybody remember? Which one do you flip to get secant? Cosine. And cosecant is the reciprocal of which function? Sine. Now, think about cosine and sine. Do they ever cross the x-axis?
Yes.
Yeah.
Basic one, yeah.
Yeah, this is the basic one. Yeah, they do cross the x-axis. When a function crosses the x-axis, what is its y value?
0.
0. So if these graphs cross the x-axis, which they do, it means they are going to hit a value of 0 somewhere. What would happen if we try to plug in a 0, which it will be at some point, right there?
You'll be undefined.
It would be undefined, and what would that cause to happen in our graph?
Vertical asymptote.
Right, we're going to have vertical asymptotes. Okay, so let's look at the graph of secant. Okay, there are many vertical asymptotes. So the graph of secant and cosecant are going to look very similar. They're these kind of U shapes and N shapes. Okay, just to be clear what one cycle is, okay, I'll trace one full cycle. That's a half cycle. That's a full cycle. One complete U and one complete N shape makes a full cycle. Okay, so now let's label these asymptotes like we did yesterday. A, B, C, D, E, F. And let's label our sections. Sections 4 and 5 together make up a full cycle. We have to decide how many asymptotes there are in sections 4 and 5. Okay, so here's what we're focusing on. There's 3 asymptotes that are possibilities here. We have C, D, and E. Those are all the asymptotes in sections 4 and 5. Out of those 3, how many do you think belong to sections 4 and 5?
2.
Only 2, right? If you said C, D, and E all belong to section 4 and 5, then what would happen when you look at sections 2 and 3? Would you say A, B, and C all belong to 2 and 3? No, you can't, because C, D, you can't use C twice, right? So it doesn't matter how you think of it, as long as you understand there's only 2 asymptotes per cycle, not 3. Okay. We could say C, well, we could say the one to the left is the one we always use. So C belongs to section 4, D belongs to section 5. E would belong to section 6. Okay, so if you're in section 6, look to your left. That tells you the one that belongs to you. Okay? However you want to think of it. Just understand there's only 2 per cycle. And then since sine and cosine look very similar, secant and cosecant look extremely similar. Remember, the difference between sine and cosine is they're just off 90 degrees from each other. And that's exactly what these are. These 2 graphs are horizontal shifts of each other. That's the difference. And as far as where you get asymptotes, well, if you wanted to figure out what your asymptotes are for cosecant, look at what's in the bottom of the fraction. Sine. Draw a picture of sine. and mark everywhere that it crosses the x-axis. So think of sine. It crosses the x-axis at 0, 1 pi, 2 pi, 3 pi, 4 pi. That's where it crosses. That's how I came up with these asymptotes. Okay. For secant, you would look where cosine crosses the x-axis. Everywhere that cosine crosses the x-axis, that's where you're going to get a 0. And if you try to divide by 0, that's where you get a vertical asymptote. Okay, so let's think of cosine. Pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. That's where cosine crosses the x-axis, and that's where all your asymptotes are for the graph on the left. So we're not going to do as much sketching of these graphs, but what I might ask you to do is tell me where the asymptotes are. So I'm going to give you a chart that tells you where the asymptotes are for all 4 functions that have them: tangent, cotangent, secant, and cosecant. It's going to be kind of like that table we used for sine and cosine. Those tables were the starting points. If you know where the asymptotes start, then you can figure out where they move to if you stretch them or shift them. You just need to know where they started. And that's what I'm going to give you a table for. Now, some functions have 1 asymptote per cycle, tangent and cotangent. Others have 2 per cycle. So sometimes you have to find 1, sometimes you have to find 2. Depends on which trig function you're doing. For tangent, the very first positive asymptote that you will hit is pi over 2. That's the original first asymptote for tangent. If we go back, I think I still have the graph of tangents. Well, I don't have the graph, but I have it written. Pi over 2 is the very first positive asymptote. Okay, that's what I'm giving you, the very first one for every graph. How about for cotangent? What's the first asymptote that you hit? We'll say it this way. The first one you hit that's not negative. 0. Yeah, it's not positive. It's not negative. So 0 is the first one for cotangent. How about for cosecant? What are the first 2 asymptotes you hit that are not negative? 0 and pi. And for secant, what are the first 2 asymptotes you hit that are not negative? Yeah, so basically everything that I put those boxes around, that's what's in this table. These are the original first asymptotes you hit that are not negative. Give people a second to copy that. All right, so now, let's say I want you to figure out the new asymptotes. Well, let's look at tangent. Or cotangent, doesn't matter which graph we look at. Here is your first asymptote, pi over 2. Here's your second one. Here's your third one. When you have an asymptote, does it repeat regularly, or is where the asymptote repeats random? It's very regular. So as long as you know one asymptote, you can describe where they all are because they repeat very consistently, very regularly. To get from here to here, you have to travel one what?
Pi.
I'm thinking more of a word, but the distance of it is pi. Yes, yep. You have to travel one period or one cycle. To get from here to here, you have to travel one cycle. So if you know the length of that cycle, you can predict where every single asymptote is going to be. Just tell me where this one starts, and then explain to me that it repeats every single cycle, both to the right and to the left. So how do we write that down? Let me show you. So the first thing we have to do is I have to show you how to find at least one new asymptote. I just have to show you how to find one. The one that I'm going to show you how to find is this one. If we shift or stretch, I'm going to show you in a minute how you find where this asymptote moves to. If you know where that one moves to, then you know where they all move to, because they're all going to move together. They're all going to do exactly the same thing. So you just have to find one new asymptote and then tell me that that asymptote repeats forever. That's how you write it repeats forever. You put plus the period times n. Kind of like we did right there. That's exactly what you would put. Okay. You have to figure out what the period is, though. If it's, maybe it's pi, maybe it's 2 pi. It depends. If you change the period in the problem, we have to figure that out. Okay. So let's look at cotangent. First thing I need to show you is how do you figure out where that single asymptote moves to? I haven't shown you that yet. Figure out where that moves to, and then you're going to know its new location. Once you know the new location, tell me that that asymptote at the new location repeats every single cycle. Same thing for these two, except you have to figure out two of them. You have to figure out where that asymptote is going to move to, and then you have to figure out where that asymptote is going to move to. Once you know the two new locations, tell me that those two new asymptotes repeat every single cycle. Okay? And it's the same thing for cosecant. You have to figure out the two new locations of the original asymptotes, and then tell me that those repeat forever. Okay, so this at least gives you a chart. So now you have all the original asymptotes in one area. What I haven't shown you how to figure out yet is that. How do you figure out where the original asymptotes move to? Okay, that's what I'm going to show you right now. And luckily, it's the same. It's the same steps no matter which trig function you're doing. To figure out where the asymptote moves to, it's the same for all of them. Does everybody have that table? Okay. Now, let me go back to what I skipped earlier, which is this. How do you find, I can even add in the word new. How do you find the new asymptotes for any trig function? Okay, like I said, it works for all of them. First, you have to find all the asymptotes in one original cycle. You already have that. Step one is already done for you. It's the table I just gave you. You already know all the asymptotes in one cycle of the original. Look at the table. So if we were doing tangent, we would be working with pi over 2. That's the asymptote in the original cycle. So that's step one. Step 2. Set the original argument, and again, that's what you're going to get from the table. Set that original asymptote equal to the argument and solve. And remember, where in a trig function, where is the argument? It's what's inside the what? It's what's inside the parentheses. So if you're looking at this, that is the argument. In other words, C and D have nothing to do with asymptotes. Okay? C and D have no effect on asymptotes, just the A and the B. So set the number from the table, the original asymptote, equal to the argument, and solve. And then this is what I already gave you in the table. That's the notation for how you write the new asymptote. It's the new one plus the period times n. Putting plus the period times n is a way of representing that it repeats forever. Because since it repeats forever, we can't write every one of them down. There's infinitely many. But we can write something that represents all of them. And that's how you do it. Okay, so all the numbers in that black box, the x1 and x2s, they are figured out in that step right there. Step 2. So now we're going to practice just trying to do a few things with these other 4 trig functions. As I said, sketching is not really going to be something that we go into, right? Because these are a little harder to sketch. I'm going to ask you different questions, or I might give you pictures and have you match graphs, like we did in the lesson earlier. But you are not going to have to sketch these from scratch. Okay, does everybody have that? Bless you. All right. So this one says find the domain, the range, period, and the vertical asymptotes of, well, I guess we can start with that. There's no transformations. That's just basic secant. I do want to do one with a transformation after. Start with the period. Let's go back and look at the picture of secant and see if we can measure on the grid how far apart 2 cycles are. Okay, so that's for secant, so I'm going to go back to the graph of secant. Okay, secant is the one on the left. Let's make that bigger. Okay. 1 full cycle would be from, let's say, like C to E. That's the length of 1 cycle. In other words, it's the distance between 2 asymptotes. 1, 2. We've got some asymptotes right here. Let's find the distance between 2 of them. This one, 1, 2, and that one. So I'm really finding the distance between asymptote D and F. But that's fine. It's the same thing. You just have to find the distance between 2. All right. If you want to find the distance between 2 numbers, what do you do with them? Subtract them. So let's take, what was it 5 pi over 2 and 1 pi over 2. What's 5 pi over 2 minus 1 pi over 2?
4 for 2.
4 pi over 2,
And 2 pi.
which is 2 pi. The length of the period is exactly the same as it is for sine and cosine. And I wrote that down right there. Find the period of secant or cosecant. It's exactly the same formula as sine and cosine. So basically, every trig function uses 2 pi over b, except tangent and cotangent. Tangent and cotangent uses pi over b. Yep. All right. So now let's fill in our period length. What's b in this problem right here?
1.
1. So there is no change to the period. So it's 2 pi divided by b, or 2 pi. So that's my period. Okay, let's do the range next. Okay, range is how high and low the graph is going to go. So look at secant. Just so it looks a little cleaner, I'm going to erase some of that. How high does it look like the graph goes? Forever. How low? Forever. Does it hit everything in between? No, there's a gap. Right? Where is the gap? It's right in here. So the range is everything from this number down and that number up. And then there's a gap in the middle. Anybody have a guess how high that bottom section goes? Yep, it goes right up to -1. It's basically the opposite of the range of sine and cosine. Sine and cosine is between -1 and 1. This is everything outside -1 and 1. So how would you write down from -1 going down forever?
Negative infinity with the parentheses, comma, -1 and good.
Yep. So that represents everything under -1. How would you represent everything above? Well, I didn't ask you yet, but how low do you think that point goes right there? 1. So how would you represent everything from 1 and up?
1, 2, infinity.
And what else would we need there? Bracket and parenthesis. So that is your range. Okay, asymptotes. Okay, so the way that we're going to write the asymptotes is exactly the way I explained them right here. Are there any transformations happening in this one? No. So then, essentially, the new value right here is going to be exactly the same as the old value. All we have to do is put plus the period times n. Okay, so we're doing secant. What are my 2 original asymptotes for secant?
Pi over 2 and 3 pi over 2.
Pi over 2 and 3 pi over 2. No transformations are happening. So these are going to be the 2 new asymptotes. Nothing's changing. Pi over 2 and 3 pi over 2. Usually we put x equals because it is a vertical line. Now, if you write that, you've only told me 2 asymptotes. But how many asymptotes does this graph really have? Infinite. So you have to tell me that each one of those asymptotes repeats forever by putting this on the end of it. Plus the period times n. So plus, what did we say the period was earlier? That's why I do the period first. 2 pi n and 2 pi n. So that means the next copy of this asymptote will occur at that number plus 2 pi times 1. The next copy will occur at that number plus 2 pi times 2. And the next one after that will be where it started, plus 2 pi times 3. Okay, and same thing for the one below it. That's the first copy of the asymptote. The next one is at that number plus 2 pi. The next one is that number plus 4 pi, plus 6 pi, plus 8 pi. It's going to keep repeating every 2 pi. So that's how you write your asymptotes. And then once you do that, the domain is everything that's not the asymptotes. And that's exactly what I'm going to write down. So the domain, it's all reals except the asymptotes. So that means if you find the asymptotes wrong, then yes, your domain is also automatically wrong. But the domain is everything that's not an asymptote. Just make sure you get the asymptotes right. Okay, and that's the kind of stuff that we're going to do with these 4 trig functions. No graphing by hand. But that's all the information you would need to figure out the graph by hand. We just don't do that. Okay. Questions on any of those 4 things? Okay, so let me see. That's kind of what we did in last night's homework. Okay, we can try this one real quick. It's cosecant. It's almost the same as secant. Shouldn't take us as long. Okay, what's the period of cosecant? What's the formula to find it?
T equals 2 pi over
2 pi over b. Any transformations in this one?
Yeah.
Nope. So b is 1. So the period is 2 pi. Okay, let's do the range. Luckily, if you get the range wrong, it doesn't affect anything else. If you get the period wrong, it affects other things. So that's an important one to get right. Okay, so cosecant. How does the range of cosecant compare to the range of secant?
Same.
It's the same. So I'm just going to write that. It's the same. Okay, same range. So negative infinity to negative 1. 1 to infinity. Okay, range. Asymptotes. First, how many asymptotes are there per cycle in cosecant?
2.
2. So we need to write 2 answers. Again, are there any transformations? No. Then we don't have any changes in the original asymptotes. What are the 2 original asymptotes for cosecant? 0 and pi. 0 and pi. If you just write 0 and pi, you've only told me 2 asymptotes. I want to know every asymptote. So what do we put on the end of each one of them?
Plus 2 pi.
Yep, plus 2 pi n. And yes, adding 0 there doesn't really do anything. You could just put 2 pi n, and it would be the same thing. And then the domain would be?
All real numbers except the asymptotes.
Right, all real numbers except any of these ones that we just wrote down. I want to try one now where the asymptotes move, okay? Because I did all that table stuff to show you how to figure that out. We haven't done one yet. So this one, they just want the period and the asymptotes. You need the period to do the asymptotes anyway. So even if it didn't say find the period, you would have to. And then we're going to sketch it, but on a calculator. So let's start with the period. What's the formula for the period of a cosecant function?
Pi. 2 pi over b.
2 pi over b. It's always 2 pi over b unless it's a tangent or cotangent. Always 2 pi over b. So period is 2 pi. And this time there is a transformation. What's b?
3.
3. That's the new period. It got compressed by a factor of 3. Okay. Now, the asymptotes. First thing I need are the 2 original asymptotes for cosecant.
0 and pi.
0 and pi. Okay. So over here, I'm just going to put the originals. That's not the answer they want. They want the new ones, but let's start with the originals. 0 and pi. Okay, let's go to our directions. It says find the original asymptotes. Okay, did that. Set each asymptote equal to the argument and solve. So now let's do that. What is the argument in that equation? 3x. You're going to set each asymptote equal to 3x and solve. That's going to tell me the new location of each of those asymptotes. How do we get x by itself in the top? Divide by 3, divide by 3, and 0 divided by 3 gives me 0. In other words, that asymptote didn't move because it was at 0. It stayed the same. All right, let's look at the bottom one. How do we get x by itself there? Divide by 3, divide by 3. So the asymptote that was originally at pi is now where? It was compressed by a factor of 3. So now, instead of being pi units, it's at 1/3 pi units, pi over 3. Okay, now, if that's all you write, all you've done is tell me 2 asymptotes. I want to know every one of them. So in general, how often do each of these asymptotes repeat? Every what?
Cycle.
Every cycle. So we need to put plus the cycle times n. What is the cycle for this graph?
2 pi over 3.
2 pi over 3. So this first asymptote will start at 0. The next one will be at 2 pi over 3. The next one will be at 4 pi over 3, 6 pi over 3, 8 pi over 3, 10 pi over 3, forever. So that's how you write down your new asymptotes. Okay. Any question on that? Let's just say, I don't want to go through a whole problem, but let's just say I had tangent 2x, and I wanted to know just where the original asymptote is going to move to. What's the original asymptote for tangent 2x?
Pi over 2.
The original is pi over 2. What would we set that equal to know where that moves to? You'd set it equal to the argument. And how would you get x by itself? You divide by 2. So the asymptote that was at pi over 2 is now going to be at pi over 4. That's where the original asymptote moves to. Now the easy part, you just put plus the period times n to tell me that it's going to keep repeating itself. And the period in this case would be, what is the period? Remember, it's a tangent function. Pi over 2. Remember, the formula for tangent is pi divided by b, and b is 2. So you'd put plus pi over 2 n. That's how often it repeats. And there's only one, because it's tangent. The only time you have to do 2 are secant and cosecant. All right, so let's finish up with something we pretty much did yesterday, solving again on the calculator. This time I might give you a tangent one, or a cotangent, or a cosecant to solve. Now, yesterday I might have given you something like this. Actually, let me do zoom 7 so I can zoom out. Okay. I gave you something like that, and I gave you a section to zoom in on and say, find the answers in that section. In reality, if I didn't have you zoom in, but I could have you zoom out forever, how many times would the wave and the line cross?
Forever.
Forever. Okay. So what we're going to look at to write our answer today, we're still going to do the same thing we did yesterday, but I'm going to want you to represent every single answer rather than just 2. Representing every answer or just 2 answers is the same amount of work. It's just how you write your answer when you're done. Okay. So we know that if you can find one solution to a trig equation, technically there are infinite solutions. Because if you zoom out far enough, you'll see that same solution again in the next cycle, and the next cycle, and the next cycle. You'll just keep seeing it. Just like that. Keep seeing the same answer repeated over and over. So to represent all solutions rather than just 2 specific ones, you find one of the solutions like we did yesterday using second calc intersect. But then instead of just writing that number, do what you did with the asymptote. Tell me that that number repeats every cycle. You put plus the period times n. Period times n is how you always represent something repeating forever. Whether it's an asymptote or an intersection point, it doesn't matter. That's how you represent repeating forever. Okay, so it's the same amount of work really as yesterday. Find the intersection point, or if there's more than one, find both, and then just put plus the period times n. All right, let's try that one. Okay, where is the cosecant equal to negative 1.6? Okay. First of all, I don't have a cosecant button. But I do know that cosecant is which trig function flipped? The sine. That's how you have to type in cosecant. Just like that. 1 over sine. What's going to go on y2? Negative 1.6. That's how you type that in. Now we hit graph. Now the problem with the graph I'm going to have right here is I'm zoomed out pretty far. Because I'm zoomed out so far, you're going to see lots of solutions. Okay? If we had zoomed in, it would have made it easier to focus on the 2 solutions that we really need. What's the period of cosecant? 2 pi. Then let's not be zoomed out so far. Let's set our window so we're zoomed in to exactly 1 cycle, because that's all we need to do. Find all the solutions in 1 cycle. If you're zoomed out and you're looking at 3 cycles, you're going to get confused. So zoom in to 1 cycle. Now let's look at the problem. 1 cycle should be a full U shape and a full N shape. Those are the answers we want to focus on. We're going to find the 2 answers in 1 cycle. That's exactly what you did in the homework last night. So second calc intersect. I think we might have to be a little bit careful. Make sure you put your cursor on the bottom part of the graph, not the top. So one answer we get is 3.82. second answer. Second calc intersect. Does it matter where I put my guess? Yeah, I need to put it a little closer to the other one. 5.61. Okay, so we have the two answers in the first cycle. That answer is going to repeat again, in general, how much later?
2.5
I think even more general for now.
after 1 cycle.
After one cycle. That's always how a trig function works. That answer is going to repeat in another cycle. So is that first answer. Now I need to know specifically what is the cycle for cosecant. No transformations.
2 pi.
So we're going to put plus 2 pi n plus 2 pi n. That means the next time you will see this answer that's highlighted will be 5.61 plus 2 pi. If I drew the next cycle and did the intersect, it would be at 11.89. The next time you would see the answer after that cycle would be at 18.17. And again and again. That's the same answer every 2 pi units. And that's how you represent all of them, just like that. Any question on that? Yeah.
My calculator doesn't show the cosine or cosecant for some reason. Like on the graph, it just doesn't show it.
And you set your window and your mode to everything that we needed?
Yeah.
You're in radians?
Maybe.
No, you're in degrees.
Oh, is that it?
Yeah. Yeah. Got to make sure if you're doing things with 2 pi, you're in radians. If we were using 360s here, then degrees would have been okay. Let's try. Yeah, I might as well see if we can do that last one real quick. Okay. It says find all solutions. Not one, not two, all of them. So that means you need period times n. We could start with that. What's the period of the tangent function without any transformations? Pi. So we know period times n is going to be part of our answer. What I need to figure out, though, is what's the first answer. Without the first one, I can't tell you where it repeats because I don't have a starting point. So what would we put in y1?
Tangent of x.
Yep, and in y2?
2.5.
2.5. Okay. Let's set our graph to one cycle. If we're zoomed out, we're going to see lots of answers. So we just said one cycle is how big? Pi. So the easiest way, I would just go 0 to pi on your screen. Hit graph. We're going to break the tangent cycle into 2 sections, but that's fine. That's one full section. And how do we find where it hits it?
Second calc intersect.
Second calc intersect. All right, I wasn't careful enough with where I put my cursor. Since it's in 2 pieces, you do have to move it until you see it. 1.19. How much later would the next answer occur?
1 period later.
1 period, which is how much? Pi. The next answer should be at 4.33. Well, let's check it real quick and see if the next one is 4.33. If it is, then we know we did it right. This is the one I'm saying should be 4.33. Second calc intersect. Yep, 4.33. And then the next one after that would be another 3.14. So if you just keep adding 3.14, you'll get all your answers. All right, and that's 6 1. Okay, so let me just double check that. 3 and 6, those are just matching. 7 through 10, that's all on the calculator. You just have to write down a window. 13 and 15, these two ask you to sketch. I want you to do everything in the question, but you do not have to make a sketch. So find domain, range, period, and asymptotes. No sketch. That one. And that one. And, okay, 29, 31, that's what we just did on the calculator. And then 34, that's also on the calculator. And okay, so that's good. So 3 through 6, 7 through 10. 13, 15, no sketch. And then 29, 31, 34, and 46 to 48. I will put the topics for the test at the end of the video while you are at lunch.